Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 1689, partitioning into minimum number of Deci-Binary numbers. In this session, we'll break down the problem, explore possible approaches, and discuss the optimal solution. Let's get started. In this problem, you're given a string n that represents a positive decimal integer. Your goal is to determine the minimum number of positive Deci-Binary numbers required to sum up to the value of n. Now, a Deci-Binary number is a special type of number that only contains the digits 0 and 1. For example, 0, 1, 10, or 101 are all valid Deci-Binary numbers. You can use multiple Deci-Binary numbers in combination to achieve this sum. The input to the problem is a single string n, and the output is an integer representing the minimum number of Deci-Binary numbers needed. Let's look at an example where the input is n equals 32. The output for this example is 3. This means we need at least 3 Deci-Binary numbers to sum up to 32. Here's how we can achieve this. One possible solution is to use 11 plus 10, which equals 32. Another way could be to use 1 plus 30. In both of these cases, the minimum number of Deci-Binary numbers required is determined by the largest digit in n. For the given input 32, the largest digit is 3, so the answer is 3. Now, let's consider another example where the input is n equals 82734. For the input n equals 82734, the output is 8. In this case, the largest digit in the number is 8, which means we need at least 8 Deci-Binary numbers to form the value 82734. This is because each Deci-Binary number can only contribute a maximum of 1 to each digit position. For example, if the largest digit in n is 8, then at least 8 such numbers are required to fully account for that digit. Similarly, for another input, such as n equals 273, the principle remains the same. When n equals 273, the output is 7, which is the largest digit in the string. This tells us that at least 7 Deci-Binary numbers are necessary to sum up to 273. The constraints for this problem specify that the length of n can be as large as 10⁻⁵, and n will only contain numeric digits without leading zeros. The key insight here is that the minimum number of Deci-Binary numbers required is always equal to the largest digit in the string n. This is because no single Deci-Binary number can contribute more than 1 to any digit in a specific position, so the largest digit effectively sets the lower bound for the number of such numbers required. To start, let's consider a brute force approach to solve the problem. The key intuition here is that Deci-Binary numbers only consist of digits 0 and 1, so we can simulate the process of repeatedly subtracting the largest possible Deci-Binary number from the given number, n, until n becomes 0. Each subtraction essentially represents a single Deci-Binary number. To implement this, we can convert n into an integer and construct the largest valid Deci-Binary number that's less than or equal to n. We then subtract this number from n and count how many iterations it takes to reduce n to 0. However, this approach is highly inefficient. Constructing each Deci-Binary number involves iterating through all the digits of n, which takes d time where d is the number of digits in n. In the worst case, this process could repeat up to n times, leading to an overall time complexity of n*d. This makes the brute force approach impractical for large inputs, as it performs a lot of unnecessary operations without leveraging any deeper insights about the problem. Now, let's explore a more optimized approach that makes use of a critical insight about the problem. The minimum number of Deci-Binary numbers required to sum up to n is determined by the largest digit in n. The reasoning is simple: each Deci-Binary number can contribute at most 1 to each digit of n. So, to fully construct a digit like d_i, at least d_i Deci-Binary numbers will be needed. For example, if n is 82,734, the largest digit is 8, and at least 8 Deci-Binary numbers are required to form n. To implement this, we convert n to a string, iterate through its digits, and find the maximum digit. This maximum digit directly gives us the answer. The beauty of this approach is its efficiency. Finding the maximum digit only requires a single pass through the number, making the time complexity d, where d is the number of digits. The space complexity is 1, as we don't need any additional data structures. This method is not only simple but also avoids unnecessary computations, making it highly efficient. Finally, let's briefly discuss an alternative mathematical approach to reinforce our understanding. The idea here is to formally prove that the maximum digit in n is always sufficient to determine the minimum number of Deci-Binary numbers. Since a Deci-Binary number contributes exactly 1 to each digit, the cumulative contributions of multiple Deci-Binary numbers can never exceed the maximum digit in n. While this formal proof is insightful, it doesn't directly contribute to the implementation and is more suited for theoretical validation. Ultimately, the optimized approach using the maximum digit is the best strategy for solving this problem. It's straightforward, efficient, and leverages the core insight of the problem. By avoiding unnecessary computations, it achieves a time complexity of O(d) and requires no extra space, making it suitable even for very large inputs. The brute force approach, while conceptually simple, is computationally expensive and infeasible for large numbers. Similarly, the mathematical proof, though valid, is not practical for coding. By focusing on the maximum digit, we achieve an elegant and efficient solution to the problem. To solve the problem of determining the minimum number of Deci-Binary numbers required to sum up to a given integer n, let's first understand the brute force approach. The idea here is to repeatedly subtract the largest possible Deci-Binary number from n until n becomes 0. Each subtraction represents one Deci-Binary number used. We start by accepting the integer n as input and initializing a counter, count, to 0 to keep track of the number of Deci-Binary numbers used. At each step, we identify the largest Deci-Binary number that can be subtracted from n. To do this, we extract the largest digit in n, which we call max_digit. Using this digit, we construct a Deci-Binary number where each digit matches the corresponding digit in n if it is 1, and is 0 otherwise. For example, if n is 4321, the largest Deci-Binary number is 1111 because it allows us to subtract 1 from each digit of n simultaneously. After identifying the largest Deci-Binary number, we subtract it from n and increment the counter, count, by 1 to indicate that one Deci-Binary number has been used. This process is repeated until n is reduced to 0. Once n reaches 0, the value in count represents the minimum number of Deci-Binary numbers needed to decompose n. The algorithm implementation involves iterating through these steps, finding the maximum digit in n, subtracting the corresponding Deci-Binary number, and incrementing the counter. This approach ensures that we systematically reduce n while counting the necessary Deci-Binary numbers. For instance, if n is 4321, we see that 4 iterations are required to reach 0, which means 4 Deci-Binary numbers are needed. While the brute force approach works, it involves repeatedly simulating the subtraction, which can be optimized further. The key insight here is that the minimum number of Deci-Binary numbers required to decompose n is directly determined by the largest digit in n. This observation simplifies the problem significantly. Since Deci-Binary numbers contain only zeros and ones, they can only reduce each digit of n by at most 1 in each step. Therefore, the largest digit in n dictates the minimum number of steps required to reduce n to 0. For example, if the largest digit in n is 5, it will take at least 5 Deci-Binary numbers to reduce that digit to 0. This means that instead of simulating the subtraction repeatedly, we can simply identify the largest digit in n and return it as the result. This optimized approach avoids unnecessary computations and provides the answer directly. To implement the optimized approach, we first read the input n as a string. This makes it easier to extract and compare digits without performing arithmetic operations repeatedly. The largest digit in the string representation of n is then identified, and this value is returned as the result. For instance, if n is 4321, the largest digit is 4, which means the output is 4. This simplified method eliminates the need for iterative subtraction and reduces the complexity of the solution. Using string representation also allows for straightforward digit extraction and comparison. This approach handles the input efficiently and ensures correctness, regardless of the size of n. The optimized algorithm is not only straightforward but also highly efficient in terms of both time and space complexity. Since we are only iterating through the digits of n once to find the maximum, the time complexity is O(d), where d is the number of digits in n. The space complexity is O(1), because no additional storage is required. In comparison, the brute force approach has a time complexity of O(d*k), where k is the maximum digit in n, due to the repeated simulations of subtraction. Both approaches require no extra data structures, which ensures constant space usage. Considering edge cases, for a single-digit input, the output is simply the value of n itself. For example, if n is 7, the result is 7 since it only takes one Deci-Binary number to represent a single digit. When all digits in n are the same, the result is equal to that digit. For example, if n is 2222, the output is 2 because it takes two Deci-Binary numbers to reduce each digit to 0. For large values of n, the algorithm remains efficient due to its linear dependency on the number of digits. The optimized approach ensures that even for very large integers, the solution is computed quickly and without additional overhead. This makes it robust and suitable for a wide range of input sizes, highlighting the power of simplifying problems through mathematical insights. This solution determines the minimum number of Deci-Binary numbers required to sum up to the given integer n. Here's the explanation. 1. The problem can be simplified by recognizing that each Deci-Binary number contributes at most 1 to each digit of n. Therefore, to represent a digit d in n, we need at least d Deci-Binary numbers, because no single Deci-Binary number can contribute more than 1 to a single digit. 2. The key insight is that the minimum number of Deci-Binary numbers needed is equal to the maximum digit in the string representation of n. For example, if n equals 82734, the maximum digit is 8. This means we need at least 8 Deci-Binary numbers to construct the sum. 3. The code iterates through each character, digit, in the string n, converts it to an integer, and finds the maximum value among these digits using the max function. This gives the result directly. 4. The function returns the maximum digit, which is the answer to the problem. This implementation has a time complexity of O(k), where k is the number of digits in the string n. It is efficient and handles all edge cases, such as strings with only one digit or strings with all identical digits. This is the Java implementation for LeetCode problem number 1689, partitioning into minimum number of Deci-Binary numbers. The solution mirrors the Python implementation by iterating through each character in the input string, converting it to an integer, and tracking the maximum digit. Key Java-specific details include the use of char to represent characters and math.max for comparisons. The final result, representing the minimum number of Deci-Binary numbers needed, is the maximum digit in the input string. This problem challenges us to find the minimum number of Deci-Binary numbers needed to sum up to a given positive integer n. A Deci-Binary number is a number made up of only the digits 0 and 1. The key insight here is that the number of Deci-Binary numbers required is equal to the largest digit in n. This is because each digit in n contributes that many 1s to the sum, distributed across the Deci-Binary numbers. For example, consider the case where n is 32. First, we process the input, which is given as a string. To find the solution, we iterate over each digit in the string, identify the digits 3 and 2, and compute the maximum value among them. The maximum digit, in this case, is 3, so we need 3 Deci-Binary numbers to represent n. Once the maximum digit is determined, we can directly output the result. For n equals 32, the minimum number of Deci-Binary numbers required is 3. Now, let's look at another example where n equals 82734. Here, we again process the input as a string and identify the digits 8, 2, 7, 3, and 4. To determine the maximum digit, we compare them step by step. Starting with 8 and 2, the maximum is 8. Comparing 8 with 7, 3, and 4 still results in 8 as the largest. Since the maximum digit is 8, the minimum number of Deci-Binary numbers required to represent n is 8. This simple approach allows us to solve the problem efficiently. For another example, consider n equals 11111. Here, the input is processed as a string of digits, 1, 1, 1, 1, 1. When we compute the maximum digit, we repeatedly compare 1 with itself, so the result is 1. This tells us that only one Deci-Binary number is needed to represent n. The final output, therefore, is 1. This example demonstrates that the number of Deci-Binary numbers required directly corresponds to the largest digit in n, regardless of how many digits the number contains. The computation remains consistent and straightforward. Now, let's summarize the key observations. The reason why the maximum digit dictates the solution is that it determines the tallest column of 1s needed in the Deci-Binary representation. This approach is highly efficient, requiring only a single traversal of the digits in n, resulting in a time complexity of O, L, where L is the length of the string n. It's also important to note edge cases, such as n equals 0, which technically falls outside the constraints since n is always positive. To visualize the solution, imagine stacking Deci-Binary numbers as columns. The tallest column corresponds to the largest digit. For example, in n equals 32, the tallest column has a height of 3, so we need 3 Deci-Binary numbers. This problem illustrates how a simple property, like the maximum digit, can lead to an elegant and optimal solution. To understand the time complexity of our solution, let's first break it down into its core operations. The primary step involves iterating through the input string n, which contains the digits of the number. Each character in the string is visited exactly once as part of the generator expression max, int, digit, 4-digit in n. If the length of n is k, this results in an iteration that takes k time. Next, during this iteration, every character is converted from a string to an integer. Since converting a single character is an O1 operation, and there are k characters, this step also contributes k to the total complexity. Finally, the max function processes all the integers generated by the expression, which again requires k time because it evaluates each element once to determine the maximum. When you combine these 3 steps, iteration, conversion, and finding the maximum, the overall time complexity sums up to k. Now let's focus on the space complexity analysis. The input string n itself doesn't add to the space complexity because it's provided as input and not duplicated during the computation. The generator expression used, int, digit, 4-digit in n, is evaluated lazily, meaning it doesn't store all the integers at once, it generates each number on demand. This ensures that the generator only requires O1 auxiliary space. Additionally, the max function, which computes the maximum value, uses a constant amount of memory for its internal operations. Temporary variables used in the process also contribute only a fixed amount of space. Since no additional memory is used that scales with the size of the input, the overall space complexity of the solution is O1. Let's compare this optimized solution with a brute force approach. A naive method would involve repeatedly subtracting Deci-Binary numbers from the input until it becomes 0. This process would require generating and subtracting Deci-Binary numbers multiple times, making it computationally expensive. Specifically, for an input with k digits, the time complexity of the brute force approach could reach k asterisk value of n, where value of n is the numeric value of the input string, a much worse performance compared to the linear k complexity of our solution. The mathematical reasoning for the optimized solution is straightforward. Since a Deci-Binary number uses only the digits 0 and 1, the maximum digit in the input string dictates the minimum number of Deci-Binary numbers needed. This is because no digit can be represented with fewer Deci-Binary numbers than its own value. By directly identifying the maximum digit, the algorithm ensures we achieve the optimal result without unnecessary computations, all within linear time. When solving this problem, there are a few common mistakes to watch out for. First, some people confuse Deci-Binary numbers with binary representations. Deci-Binary numbers do use only the digits 0 and 1, but they represent base 10 values, not base 2. Misunderstanding this distinction will lead to incorrect solutions. Another mistake is overcomplicating the approach by trying to explicitly generate all intermediate Deci-Binary numbers. This is inefficient and unnecessary since the core insight is that the minimum number of Deci-Binary numbers you need is determined by the maximum digit in the number. Finally, it's crucial to consider the constraints. For instance, the input number can be extremely large, with up to 100,000 digits. Solutions that involve iterative subtraction or excessive operations will struggle with such inputs and are likely to exceed time limits. Another common issue arises with string-to-integer conversions. In many solutions, the number is treated as a string to easily extract its digits. If this step is mishandled, it can introduce bugs or inefficiencies. Additionally, some people misinterpret the problem's requirements. The goal here isn't to reconstruct the Deci-Binary numbers themselves, but instead to figure out the minimum count of such numbers required. Focusing on reconstruction rather than counting creates unnecessary complexity and often leads to solutions that are harder to implement and less efficient. To tackle this problem effectively, there's a key insight to keep in mind: the minimum number of Deci-Binary numbers required is equal to the maximum digit in the number. This stems from the fact that each Deci-Binary number can only contribute at most 1 to each digit's place. Recognizing this simplifies the problem significantly. This type of problem fits into a broader category of digit-based optimization challenges, so it's always helpful to think about operations at the digit level when working with large numbers. Don't forget to consider edge cases, such as single-digit numbers, numbers with all zeros except for one digit, or inputs with all nines. During interviews, ensure you clearly explain the reasoning behind the maximum digit insight, as it showcases your analytical problem-solving skills. Similar problems that you can explore include partitioning into minimum number of Deci-Binary numbers, remove k digits, monotone increasing digits, and maximum width ramp. There are also alternative approaches to solving this problem. One option is brute force simulation, where you iteratively subtract the largest possible Deci-Binary number from the input until the number becomes 0. While this method is simple to implement, it is highly inefficient for large inputs because it involves repeated subtraction. A far better approach is digit-level analysis, which directly identifies the maximum digit in the number and uses that as the result. This method is extremely efficient and operates in linear time relative to the number of digits. Another approach is greedy construction, where you iteratively build Deci-Binary numbers by reducing the largest digit step by step. While this method is more intuitive to understand than digit-level analysis, it is less efficient because it involves repeated processing of the digits. Each of these approaches has its trade-offs, but the optimal solution leverages the insight about the maximum digit for simplicity and speed. Great job making it to the end. To recap, this problem was all about understanding Deci-Binary numbers and deriving an efficient solution based on the input's maximum digit. Remember the key insights and apply them to similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!